Welcome to this lesson on formal charge. So just going to go into what exactly formal charge is. So basically formal charge is the method of hypothetical bookkeeping of electrons. Now the reason why we use this bookkeeping is in order to determine the most probable Lewis structure. And just a quick rundown on what a Lewis structure is. A Lewis structure is where we include, let's do carbon right now, our first atom, or our atom right here. We have the chemical symbol surrounded by its valence electrons. Here we have carbon, and if we were drawing for methane, we would just H, right? Just add all of our electrons, represent them as dots, and represent all of our atoms by their chemical symbol. And these are the bonds. So what we're just really doing here is identifying that when we take a molecule, what structure is going to be most likely to be seen. Now the way that we find formal charge is by taking of each atom their valence electrons minus their lone pair electrons minus 1/2 of their bonded electrons. So just a quick little example of how this works is, let's take water here. We have water H2O. Now this is a very common bent polar molecule that most people know, right? We have oxygen as the central atom and then 2 hydrogens as the terminal atoms. Now if we were to take hydrogen here, right? Hydrogen, how many valence electrons does it have on its own normally? It has 1. How many lone pair electrons does it have in this case? Well, it has 0, so minus 0. And then how many bonded electrons does it have? Well, in this bond, it really could just look like boom, boom. So it has 1 bonded electron. So minus 1, leaving us with 0. Now, for formal charge to be really most acceptable, the formal charges of each of your atoms should equate to 0. So let's go through a separate example of oxygen. We're going to ignore the second hydrogen in this case because they will both have the same formal charge, as they both have the same number of valence electrons, lone pair electrons, and bonded electrons. So now if we look at oxygen here, we can really just redraw this as being oxygen with like here, 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 because oxygen has a full octet, right? So if we look here, we say, okay, what are oxygen's valence electrons? Well, it has 6 because oxygen is the 8th element on the periodic table. Subtract how many lone pair electrons does it have? 1, 2, 3, 4. And then if we look at the bonded electrons, there are 4 electrons bonded to oxygen here from between oxygen and other atoms. And then if we divide 4 by 2, we're left with 2. And this will equate to, similar to the hydrogen, 0. And this just proves why we use this structure here as the most probable and the most common for water. Now, one crucial thing to note is that when we have a molecule with a charge on it, for example, if we look at carbonate, we have CO3 2 minus. The overall molecule here has a charge of 2 minus, which means that the formal charge of it is going to match that 2 minus. So if we take here carbonate, we're going to have this as our first example. So carbon as central atom, and then let's add some oxygens. 1, 2, 2. This is just a rough guess of what it would look like, because making rough guesses doesn't hurt as long as at the end of it you make your actual correct answer. So first we want to count the total number of valence electrons we have here. We have 1 carbon, that's 4, plus 3 oxygens, so it's going to be 3 times 6. But since it's polyatomic, having a 2 minus charge, we're going to add 2 electrons. And this will give us a total of 24, I believe. Yeah, so it's going to give us 24 total valence electrons. What I like to do is I like to count when we have this bond here. I like to count it as being one end of the line, 2 ends of the line, and each end of the line is its own electron. That's kind of just how I like to visualize it to see when I'm counting my electrons. But let's just go with it here. So if we were to fill out all the octets, we would have 2 extra electrons here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, if we count all of these here, we have 8 here, 8 here, 8 here, and 8 here. Now that's going to add to 32, which we do not want, so it means that we're going to want to put in some double bonds. Let's go here, let's go like that, just one double bond. So now if we add in our electrons, we go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Now, you can see here that I didn't have to add any other electrons onto the central carbon because when we added a double bond, like I said with counting our little dots, we have 1, 2, 3, 4 already onto it. So carbon has a full octet. Now, if we want to count the electrons here, we have 1, 2, 3, 4, 5, 6, 7, 8, and then we have 8 here, 8 here. So this does line up. We do have 24 valence electrons here, but we need to check whether or not this is the correct orientation by using our formal charge. So now let's look at the formal charge of, so we'll write Fc of subscript C for carbon. Formal charge of carbon, we have valence electrons, so 4 minus 0 lone pair electrons minus 1 over 2 times bonded, we have 4, which is going to give us 0. And next we have the formal charge of oxygen. So I'll write O1, and then I'll label this as being O1, and I'll label this as being O2, because we have 2 different oxygens in terms of orientation, so we have to do the formal charge for each. Now we have the first one, which is going to be 6 minus 4 lone pair minus 2, which is going to give us 0. But then if we take the formal charge of the second oxygen, it's going to be a little bit different. We're going to have 6 minus 6. So we're going to have subtracting the 6 lone pair electrons minus 1 bonded electron. Now this would be repeated twice by having a second oxygen like that. So formal charge of O2. Again, 6 minus 1 equals -1. So you can see here that when we add up all of total formal charges, we have 0 plus 0 minus 1 minus 1 for 4 molecules or 4 atoms total in the molecule, which leaves us with -2. And you can see that this is the correct orientation of our molecule because our formal charge, although it's not 0, it is -2, which aligns with the charge of carbonate being 2 minus. So what we would do now is when we have this molecule here, we're not done yet, right? We have it over here and it looks great, but we need square brackets around it because it has a charge and we want to write the charge outside of it, just like that. So over here on the right, this is our finalized carbonate molecule. So just finishing up this lesson, we're just going to tackle another quick example here where we have BrCl2 with an overall charge of -1. Okay, so starting off here, we're going to use our rules and see that which atom between bromide and chlorine is more electronegative. So if you look at your periodic table, you will see that it is 2.96 on bromine versus 3.16 on chlorine, which means that bromine is going to be our central atom. So if we take here bromine, and then, like I said, you can always just do a rough sketch, chlorine and chlorine, and then if we want to count our total valence electrons, we're going to have valence electrons, let's write T for total, is going to equal 7 on bromine plus 14, which is 2 times 7. And then we're going to add another one because the total charge is 1 minus, which will get us to 22 total electrons in the molecule. We go 1, 2, 3, 4. If we just want to roughly kind of estimate here, because like I said, it doesn't hurt at all to draw a rough sketch. If we want to count how many total electrons we have here once we filled all the octets, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20. We only have 20, which means that we're missing 2. Now, we haven't quite looked at this case, but when we're missing electrons, what we can do is we can see, okay, where is our central atom placed on the periodic table? And if we were to pull the periodic table, we'd see that it is towards the end of period 4. So, what we know about that is that it can have an overfilled octet. So, we have 20 electrons total in this kind of workshop molecule. What we can do here is add another 2, 1, 2. So we can just go 1, 2. That looks better. So over here, now we have 22 valence electrons, but using formal charge, we need to check, does this actually work? So if we go over here and we'll first do the formal charge of chlorine, which will give us how many valence electrons do we have to start? We have 7. Lone pair electrons, we have 6. And then bonded, we have 1. There, that will give us 0. Formal charge of, I'll just do the second chlorine as well, which is going to be 7 minus 6 minus 1 to get us 0 again. And now for bromine, formal charge of bromine. We have 7 minus 6 minus 2 to give us -1. Now if we add all our formal charges, we have 0 plus 0 minus 1 with a sum of -1, which you can see matches the charge of the molecule to prove that this here is our correct orientation, but we're not finished yet. Like the previous example, we need to put square brackets around it, and we need to give it a charge.